University. He'll talk on convex bodies and algebraic properties of graded families of ideals. And as usual, we'll have about a 40 minutes lecture and then 5 minutes break and then up to another 40 minutes lecture. And I will take care of the chat, and whenever you have a question, please write and I will direct it to Tai whenever it's convenient. Please, Tai.
Thank you, Bern. Well, thank you, the organizers, for allowing me to give my talk here, and thank you all for attending the talk. So in today's talk, I'd like to tell you about some connection between algebraic properties of graded families of ideals with combinatorial data from associated convex bodies or convex regions in more generally. So let me begin by the motivations with in a very simple setting that most of us are familiar with. So to start, I'm going to fix a field, and a lot of the results that I'm going to talk about are actually true for an arbitrary field, but I'm going to just fix a field that is algebraically closed, just to make it easy for many of the statements. And then R is going to be a polynomial ring for now. Later on, I might even use a regular local rings. And then M is the maximum homogeneous ideal. And the standard notation for monomial in R would be x to the A, where A is a vector of non-negative integers, and x to the A represent x1 to the A1 up to xd to the AD. And the one definition that most of us have seen before is the construction of the Newton polyhedron with respect to a monomial ideal. So basically, if we start a monomial ideals, you look at any monomials that sit inside that monomial ideal, look at its exponents, and that is a non-zero vector with integer entries, non-negative vector with integer entries, sorry. And we look at that as a point inside R to the D and take the convex Hall, and that is what we call the Newton polyhedron of this ideal. So let me give you an example. This is a very simple example of an ideal in two variables generated in with three generators, x to the 6 and x squared, y squared, and y to the 5th. And of course, with x to the 6, we have the point 6, 0, and then x squared, y squared, that's the point 2, 2, and then y to the 5th, that's the point 0, 5. And if we take elements inside this ideal, that basically means that we take points that are to the right or above of these generators. And then if you take the convex Hall, we basically get this region, the shaded blue region. And so I'm going to also record a notion of integral closure of an ideal, since I was told that there's might be some graduate student in this talk. So let me be very elementary here. If I is an ideal in R, then an element F is said to be integral over I if F satisfy harmonic equations with coefficients AI being inside the ith power of the given ideal I. And we let I bar be the collection of all elements that are integral over I, and we call it the integral closure of I. We know that the integral closure of an ideal is an ideal itself. And the first connection between algebra and geometry, convex geometry, is that the integral closure of a monomial ideals is completely described, is actually precisely described by the Newton polyhedron. In other words, all the monomials appearing inside the integral closure, in fact, are inside the Newton polyhedron. So going back to our example, when we look at the integral closure, we actually pick out new generators. That's the point I to the 4th y and xy to the 4th. The algebraic invariance, the first algebraic invariance that I want to talk about in this talk is the multiplicity. So if we have an m primary ideals in the ring R, then the multiplicity of I is defined to be the limit of the length of R mod I to the n over n to the d mod d factorial. So if you look at the limits of R mod I to the n, of course, that's a Hilbert functions, and then eventually behave like a Hilbert polynomial. And so this is really just picking out the normalized largest coefficient, highest coefficient, not largest coefficient. And if you look at our example again, the multiplicity of this ideal is computed to be 22, and the observation is that this 22 is nothing but 2 times the area of this orange shaded area, which is the complement of the Newton polyhedron inside the first quadrant. And in fact, this happens in higher dimension as well. So this is an example in 3 dimensions. So here we have an ideal generated in x, y, and z by x to the x cubed, y squared, z to the 4th, x, y, and y, z. If we plot all these points, take points that are larger than these points, and take the convex hull, this is the region that we're going to have. So this is just a different angle looking at that. And as we have seen before, the integral closure is described by integral point in this region. And the multiplicity of this ideal is now computed to be 17, and that is actually 6 times the volume of the complement of the Newton polyhedron. So in fact, this is true in a very general setting, and says here in 88 proof that if I is an M primary monomial ideal, then the multiplicity of I is d factorial times the volume of the complements of the Newton polyhedron inside the first quadrant of R to the d. And I would write the co-volume to represent the volume of the complements of whatever that object is inside the first quadrant. So there have been a lot of generalizations of this result in various directions. On one hand, instead of looking at multiplicity and volume, one can look at mixed multiplicity and mixed volume. This has been looked at by Trung and Wemer, Sid Ruiz and Montaño, and Wemer and his student and collaborators. Another direction is to look at multiplicity of a gridded family of ideals, not necessarily just powers of the ideals. This has been looked at by Lazarsfeld-Mustara, Karaszkowski, and Kukoski. Or one can look at multi-gridded algebra instead of just gridded algebra or grid polynomial in our setting. This has been looked at by Sid Ruiz, Mohammadi, and Monin. And one can also look at the situation in positive characteristic instead of looking at gridded family of ideals. One can look at P families of ideals. This has been looked at by Hernandez, Jeffrey, Das, Tai, Nguyen, and Bing Fan. So I would point out that so here one can look at mixed multiplicity and mixed volumes, and the mixed volume here, of course, of an object that are defined similarly to the Newton polyhedron. Over here, one look at multiple family of one look at gridded families of ideals, and the geometric object would be the Newton-Okunkorf bodies, and over here the geometric object would be what they call the global Newton-Okunkorf body, and here the geometric object that they look at is the pyramid associated to the family. So my focus today would be on these directions, where instead of looking at the multiplicity of an ideal, we look at the multiplicity of a gridded family of ideals. So gridded family of ideals, of course, is a collection of ideals that satisfy the gridded conditions particularly P times IQ sit inside IP plus Q. And we have seen an example of gridded family, meaning the family of powers of an ideals. We also have family of symbolic powers or family of integral closure of powers. Those are also very familiar gridded family of ideals. So as I mentioned, the geometric objects in this line of works that have been looked at is the Newton-Okunkoff body. Newton-Okunkoff body is defined in a much more general setting when R is not necessarily polynomial ring, but rather R could be an analytically irreducible local domain. Newton-Okunkoff body is inspired by Okunkoff's works. It's systematically developed by Lazarsfeld, Mustara, and then Kovacs and Povansky, and then by Kukuski about decades ago. Generally, Newton-Okunkoff body is defined for strongly non-negative semigroups, or if you go to the algebraic side, it's defined for algebras of what they call integral type, right? And the important thing is that Newton-Okunkoff bodies are constructed based on good valuations. I'm not giving you the definition of good valuation right now. At the end of the talk, if you're interested, I can give you the definition. But these good valuations are technically quite hard to understand. Now, the theorems that have been proved is that given any gridded family of M primary ideals in R, the multiplicity of this family is defined to be the lim sup of the length of R mod IN over n to the d mod d factorial. And of course, a priori, this lim sup does not necessarily need to exist as a limit, but it was proved that this lim sup is actually a limit, and one can compute these limits by the volumes from associated Newton-Okunkoff bodies constructed from this gridded family of ideals. So in this talk, I'm not exactly talking about Newton-Okunkoff body. I'm talking about something else which is related to Newton-Okunkoff body. So let me begin that discussion, but focusing first on a more familiar setting. Again, we have monomial ideals instead of just arbitrary ideal. So here, let's start with a gridded family of monomial ideals. Then each monomial ideals, as we know, has its Newton polyhedron. So one can scale the Newton polyhedron of the nth element inside the family by n. So looking at 1 over n times np of in. And then just take the union of all of this guy. Right? So this will be a convex region, convex set inside R to the D, and it's not necessarily closed. So one can close it down, and denote it by gamma. Right. So C is just the union of the scale Newton polyhedrons, and gamma just the closure of C. This region here is convex and closed, but it's not necessarily compact. And in general, actually, it is not compact, as opposed to the Newton-Okunkoff body, where often it is compact. Right? So that's why one called the Newton-Okunkoff body for the other construction, and here we call it Newton-Okunkoff region. Limiting body, this construction here has been studied and considered by various people in different contexts. For the family of ordinary power of a monomial ideal, this is nothing but just the Newton polyhedron of the ideal itself. If one look at the family of symbolic powers, where the ideal is a square-free monomial ideals, then the Newton-Okunkoff regions or the limiting body, which are the same, is just the so-called symbolic polyhedron of this ideal. So this is an example of Newton limiting body and Newton open curve regions. If we take a monomial ideal generated by x, y, y, z, and zx, this is the Newton polyhedron, and this is the symbolic polyhedron, right? So that represent the Newton open curve region for the family of ordinary power, and this is for the family of symbolic powers. So these regions both look very nice and quite easy to understand. However, Newton open curve regions of gridded family of ideals, monomial ideals, can be as complicated as we want. In fact, if we take any non-empty closed convex set inside R to the D, provided that it absorbs R to the D, meaning if you add R to the D, the non-negative or the first quadrant of R to the D to P, it falls back inside P, then there exists a gridded family of monomial ideals whose Newton open curve region is exactly this region P that we start with. All right, so this is an example where we don't have one of these familiar family, but it's still simple enough. So we take a gridded family of ideals, which are monomial ideals, and the nth element is just x, y raised to the power ceiling of n over 2 plus 1 inside a polynomial ring in two variable. One can see quite easily that if we look at the ith element, so we start from it. Basically, we look at the lines where x plus y is at least the ceiling of n over 2 plus 1, and then we just scale down by n and take the union is exactly this region here, right? But of course, we will miss this line segment from 1/2 to 1/2 because of this 1. Whenever we scale down by n, you still get that 1 over n. And so when you take the closure, we will get everything. So this blue part here is the limiting body without excluding this like segment, and the Newton open curve region in this case would be the whole thing. And one can compute quite easily that the length of R mod in is exactly a ceiling of n over 2 plus 1, choose 2. And so if you take the limits of this length over n squared mod 2, then the multiplicity is going to be 1/4. And that 1/4 is exactly twice times the area of this triangle, which is twice the core volume of this Newton open curve region, just as what we have seen in the case for the Newton polyhedron of one ideal. More generally, if we start with a gridded family of m primary ideals, okay, and let's say that we do have a good valuations, and once again, I'm omitting what good valuations are. Let's say we have a good valuations, then we can collect the values of the nth elements inside this family, right? The value groups of the nth elements, and scale it down by n, take the union, and that's what we call the limiting body of this family with respect to this good valuation. And take that closure, the closure of that, we get what we call the Newton open curve region of the family with respect to this good valuation. And the result that was proved by Convex and Kubansky is that for a gridded family of m primary ideals in R and a good valuation, the multiplicity of the family is exactly the factorial times the core volume of the Newton open curve region. So again, it resembles exactly what we have seen in Tessier's result. So the question that I'm interested in is, well, as I mentioned, good valuations are not easy to understand technically. So are there any other convex body or convex regions that can substitute the Newton open curve regions or Newton open curve bodies to give a more accessible approach to the so-called multiplicity equal to volume formula. So this is what we call the multiplicity equal to volume formula. So are there any other construction that do not depend on good valuations? And the second question that I'm interested in is, can other invariants or property of a gridded family of ideals be understood via associated convex body or convex region of the families, of the given family? So the focus in this talk for me will be on gridded family of monomial ideals, or more generally on gridded family of the so-called Newton non-degenerate ideals. The algebraic property that I'm interested in will be the Theoretic property of the Riesz algebra. And the algebraic invariance that I'm interested in beside the multiplicity is going to be the analytic spread and the asymptotic regularity. Okay. Is there any question before I move on? You good? Okay, so let me move on to what I mentioned as the Newton non-degenerate ideals, and I'm going to abbreviate it by NND. So Newton non-degenerate ideals and associated Newton polyhedra were introduced in the context of complex analysis to study geometric invariance of the rings of germs of holomorphic functions at the origin. It has been extended to formal power series rings over the complex numbers. It has appeared in various studies, particularly in the study of core of monomial ideals, in the study of torus closures of algebraic varieties. It also appeared in the study of symmetric polynomials, Schur polynomials, symmetric McDonald and Schubert polynomials. For us, these ideals are interesting because many algebraic invariants of NND ideals are computable, and monomial ideals are NND. So particularly, this is a very natural generalization of monomial ideals. So a key fact that makes this class of ideals interesting, at least for me and for a few others that have looked at this class of ideals before me, is that in the known context or in an analytic context, an ideal is NND even only if the integral closure is a monomial ideal. Now, unfortunately, when we start looking at this class of ideals, this fact does not extend to polynomial ring. So, but fortunately, we discover that it works for regular local rings. So let me tell you how one define NND ideals that actually generalize monomial ideals in the context of regular local rings. So before doing that, let me also define what it means by monomial ideals in regular local rings. Right? So here we're going to fix regular local rings of dimension D, and I'm going to assume that it's container field. And we're going to fix a regular system of parameters, x, which is x1 up to xd. So in the case of polynomial ring, it represents x, the variables, basically. Monomials with respect to x or in x, it's just elements of the form x1 to the a1, xd to the ad, just like what we have seen for monomial inside polynomial ring. And a monomial ideal, of course, with respect to this fixed regular system of parameters, is an ideal that has a collection of generators that are monomials in x. So Hubo and Irina Swanson define the Newton polyhedron associated to a monomial ideals with respect to a fixed a regular system of parameter they actually define more generally, not just regular local rings, but for regular domains. But I'm going to focus on regular local rings here. So if we have an ideal that is a monomial ideal with respect to X, meaning it has a collection of generators that are monomials in X, then the Newton polyhedron of I is just the collection of everything, of all points that are bigger than or equal to a linear combinations of the exponents whose sum of coefficients is 1. So this naturally generalized the notion of Newton polyhedron in a polynomial ring. So what about non-monomial ideals? So again, if you start with any element inside our ring, then we can represent this element as a combination of monomials, right, whose coefficients are not inside the maximal ideals. And this representation, or the collection of monomials appearing in this representation, is uniquely determined if we only consider irredundant representation. In other words, we don't allow these monomials to divide each other. And once we look at this irredundant representation, then we call the unique collection of monomials appearing in the representation the supports of the element f. So the support of f in this case is just the collection of the exponent appearing inside its monomial representation. And if we have an ideal, any ideal inside the ring R, the support of the ideal is just the union of all the supports of its elements. So now, if we start with an ideal, then we can define the Newton polyhedron of that ideal, of course, with respect to this given regular system of parameters, to be, again, we take any point inside the support of the ideal, take the convex Hall, and that sit inside the first quadrant of R to the D. And we denote by gamma x of I. And that is what we call, or that is what is called the Newton polyhedron of this ideal. So, of course, if we start with a monomial ideals to begin with, then this is nothing but the Newton polyhedron of I that was defined by Hubel and Swanson. One interesting fact about this construction is we don't have to go through every element inside I and its supports. It's enough to consider one generating sets of the ideal I and look at the supports of each of these guys, or each of multiples of this guy, or ideal generated by these elements, and take the union of those, and then take the convex Hall. That is the same as the Newton polyhedron of I. And it also have a nice property that we see for monomial ideals, particularly if we know that the integral closure of two ideals are monomials, then the Newton polyhedron actually characterize the equalities between the integral closure of these ideals. Particularly if we know that these are monomial ideals, then the equality of the integral closure happen if and only if the two Newton polyhedrons are the same. So this is an example. I'm looking at the formal power series ring in 3 variables, x, y, z, and also look at x, y, z as the obvious regular system of parameters. And this ideal has 2 generators, x to the 4th plus x squared, y to the 5th, z to the 4th, and then y cubed z minus x cubed y z squared plus x y z cubed. And so the Newton polyhedron of this ideal, of course, because it's given by 2 generators, all we need to do is to look at the Newton polyhedron of these 2 elements and then take the union and the convex Hall, and this is what we get, right? So this would give us 2 points, and then everything above this 2 point, this would give us 3 points, and everything above on of this 3 points, and then check the convex Hall. This is what we have. This is not very nice picture, but it's give you a rough ideas of how the Newton polyhedron is found. Okay, so let's move on to define NND ideals. Suppose that we start with a closed convex set inside the first quadrant of R to the D. Then we can look at the cone over this convex set with the vertex being the origin. And we can restrict everything inside the ring to this cone. In other words, we consider delta to be elements inside the ring R who sit inside this cone. And then it's not very hard to see that this ring is actually a local ring, and it has the maximal ideal being, again, the restrictions of elements inside the maximal ideals of the ring R. For any elements inside the ring R, we can look at its monomial representations and drop terms whose power are not inside the support. So we just keep terms whose power are inside the support, and we call this the restriction of G on delta. Okay, so an ideal is called Newton non-degenerate, or NND, of course, with respect to a given regular system of parameters X, if there exists a generating set G1 up to Gs, so that when we look at any compact phase of its Newton polyhedron and look at the restriction of these generators on that compact phase, it generates an ideal that is primary to the maximal ideal of this restricted local ring. Okay. So why is this called Newton non-degenerate? Well, in the analytical context, if R is the ring formal power series rings, then these conditions for being Newton non-degenerate, or at least these conditions on a compact phase delta, is equivalent to the fact that if you take any compact subphase delta prime of delta and look at the restriction of these elements inside on this delta prime, and look at the system of equations that this restriction are equal to 0, it has no common solution in C minus 0 to the D. So that's why over the compact phases of the Newton polyhedron, this system is non-degenerate. So as I mentioned, the key fact for Newton non-degenerate ideal is that an ideal is NND if and only if the integral closure is a monomial ideal, and this fact extends also to the regular local rings setting. This is an example. We have an ideal generated by two elements, x to the fifth, xy cubed, y to the fifth plus y, x cubed y. And of course, again, we pick the obvious regular system parameters. In this case, if one compute the integral closure of this ideal inside the ring of formal powers series in x and y, it is a monomial ideal. So we know that this ideal is NND. And if you go back to the original definition and look at this ideal inside the polynomial ring, it's going to satisfy the same conditions. So inside the polynomial ring, this ideal I is also an NND ideal. However, inside the polynomial ring, if one try to compute the integral closure of this ideal, we'll get an ideal that is not monomial. So that's why this result does not extend to a monomial ideals. So I think maybe this is a good time to stop for a break?
Yes, that sounds good. So maybe we meet again in 7 minutes at 50 minutes.
You meant that result does not extend to a polynomial ring. That's what you meant. You said it doesn't extend to a monomial idea. It doesn't.
That's what you meant.
Sorry, polynomial ring. Sorry, yeah.
That's what
I get confused sometimes. Yeah, thank you.
Fine, that's fine.
Mhm.
Perfect. Yeah. All right. Well, yeah. Thank you for coming back. So, as I mentioned, the introduction of NND ideals for us is to facilitate our understanding of the multiplicity equal to volume formula. But before getting to that, let me go to the algebraic property that we are also interested in, which is the Noetherian property of the Riesz algebra. So this is again a brief recall of what the Riesz algebra of gridded family of ideals is. So if you start with a gridded family of ideals, then you can just look at the direct sum of these ideals, and it sits inside the ring R at a new variable t, and that's what we call the Riesz algebra of this family. Characterizing the Noetherian property of the Riesz algebra has been a problem that is a problem that has been looked at for a long time, starting with Nagata's work. One of the familiar families that people care about is the family of symbolic powers, and the Riesz algebra of symbolic power is called the symbolic Riesz algebra. And there are actually examples of ideals whose symbolic Riesz algebra is not necessarily Noetherian. These were given by Hunicki, Roberts, and Kukuski, these examples. If we start with just one monomial ideal, then the symbolic Riesz algebra of this one monomial ideal is known to be Noetherian, and that's a result of Herzog, Hibby, and Trung. So the next natural class of ideals to look at, or family of ideals to look at, is a gridded family of monomial ideals, right? Or for us, a gridded family of Newton non-degenerate ideals. So for a gridded family of ideals, we can also construct the limiting body in a similar way as it has been constructed for monomial ideals. Basically, if we start with any ideals, a fixed regular system of parameters, then we can construct the Newton polyhedron of this ideal with respect to this fixed regular system of parameter x, and then you just scale the Newton polyhedron of the nth element inside the family by 1 over n. Take the union. That's what we call the limiting body of this family, and of course, this limiting body is dependence on x. And what we were able to prove is that if we start with a gridded family of NND ideals, then the following conditions are equivalent. The Riesz algebra of the family is invariant, or the Riesz algebra of the family of integral closure is invariant. There exists an integer c such that the integral closure of ic to the k is just the integral closure of I kc. Now, I should say that the equivalent of these three conditions actually do not require NND, right? But for NND ideals, these three conditions is equivalent to the fact that the limiting body is a polyhedron. So, this gives an interesting criteria for the Noetherian property of the Riesz algebra when the ideals are NND. What we're going to use is, of course, these results, or at least the equivalent of the first three conditions when we don't have a system of NND ideals. Okay, so now let's go back to one of our examples where the family is given by xy to the power ceiling of n over 2 plus 1. This is, as we have seen, the blue part is the limiting body without this like segment, and so it is not a polyhedron because it's not closed, right? And so in this case, the Ries algebra is not Noetherian. If we restrict to the family of symbolic powers, or we're looking at symbolic Ries algebra, then this is how the symbolic polyhedron is defined. And if we start with the monomial ideals, then this C that we have seen in our theorem is exactly the C that the Newton polyhedron of the symbolic C's power of I is the same as C times the symbolic polyhedron of I. And this C, when the ideal I is square-free monomial ideals, actually is computable by looking at the vertices of the symbolic polyhedron. So computationally, it is not hard to find this value C. Okay, and this value C can also be used to give bounds for the so-called symbolic generation type. In other words, the maximal generating degree of the symbolic Ries algebra, or the symbolic Veronese degree. In other words, is the smallest Veronese degree whose Veronese subalgebra is standard graded. So this C actually helps us also to understand the multiplicity equal to volume formula as our original goal sets for. So we prove that if we start with any gridded family, Noetherian gridded family of M primary ideals, and let's see be the C that we have seen in the characterization of Noetherian Ries algebra, then the following are equivalent. We have this multiplicity equal to volume formula. Again, the multiplicity of the family is d factorial times the volume of the complements of the limiting body inside the first quadrant. So this looks very similar to what we have seen in Tesser's results, in Convex and Kubansky's results. The difference here is this body here is constructed independent of any good valuations, right? But the trademark is it doesn't always work. This happens if and only if your family contains a subfamily of NND ideals. So I should mention that Tai is a former student of mine who's now an assistant professor at the University of Dayton. Vinh is a current PhD student of mine. He will be on the job market, so please look out for him. So let me give you an example here. So this is an ideal generated by x to the fourth plus y to the fourth, x y squared plus x squared y, and we're going to look at this ideal inside the formal power series ring. And this is the family that we look at, just the family of ordinary power of this ideal. Then when we construct the Newton polyhedron of this ideal with respect to the obvious regular system of parameter xy, this is the Newton polyhedron. And as we can see, it has three compact faces, right? And if you focus on the second compact face, there are two, and we look at the restriction of this generators, right? This generator of the ideals. If we look at the restriction of this generator on this compact face, now x to the fourth here is here, y to the fourth is here. So when you restrict to this compact face, you basically get 0. And similarly for this guy, if you restrict to this compact face, you also get, no, actually, let me see. X squared y, actually, sorry, you actually get this guy and this guy. So you get the same thing. But this system of equations has t minus t as a common solution. And you can take t to be non-zero, any value of t to be non-zero. So it violates the condition for being Newton non-degenerates, because the system has non-trivial common solution. So in this case, the ideal is not NND, and we would understand that if the ideal is not NND, then none of its power is going to be NND. So it doesn't satisfy the condition of our theorem. In other words, we should not expect the multiplicity equal to volume formula to hold for this example. And indeed, if we compute the multiplicity, we're going to get 12, and the volume, or the co-volume of this guy, meaning 2 times the volume of this, we get 11, so they are not the same. Right, so this is an example saying that if you don't have NNE ideals, unfortunately, the multiplicity equal to volume formula will not work. Let me give you a different example where it works. So this is a family again in family of ideals again in 2 variables, where I1 is given by x plus y. The even elements is just x squared plus y squared xy raised to power k, and then the odd element is just I1 times the previous even elements inside the family. So with this family, of course, because of this condition here, if you take the second Veronese subalgebra, it's just standard graded because it is the Riesz algebra of one ideal. So we know that this family is Noetherian, and C is 2. We also can see that the Newton polyhedron of the odd elements is nothing but, so I don't have a picture, but it's really just these elements above the lie, where the lie is I plus j equal to 2k plus 1. Okay. So it has one unique compact phase. And if you restrict this ideal on this compact phase, right? And the ideal here, it has generator of this form because it's I1, which is x times I, times I2k, which is x squared plus y squared and xy to the k. So the generator of this ideal has this form, and if you restrict it to this line from 2k plus 1, 0 to 0 to k plus 1, then it has, again, t and minus t with any t not 0 as a common solution. So again, this violates the condition for being NND ideals. In other words, I of 2k plus 1 is never NND. However, for this family, because of the subfamily of even elements are NND, so the multiplicity equal to volume formula should hold. And in fact, one can compute, one can see that the limiting body is just the convex Hall. Oh, I mean, it's just it's just everything above the line x plus y equal to 0, equal to 1. And the area of the triangle, as we have seen before, this is just 1/2, and 2 times it's 1, and that's exactly the same as the multiplicity. So any question before I move on? Okay, so this gives us a new understanding of the multiplicity equal to volume formula. But as I mentioned, I'm also interested in other algebraic invariants, not necessarily just the multiplicity. Particularly, one of such invariants is the analytic spread. And one can define the analytic spread of a family to be just the dimension of the fiber rings, right? So you look at the Riesz algebra mod R by m times the Riesz algebra. This invariance is finite and is bounded above by the dimension of the ring. That was proved by Kukuski and Sakar in 21. Excuse me. If the family that we start with is Noetherian, then this invariant is also known to be the same to measure the rates of growth of the number of minimal generators of element inside a family. So if in general, one can define L star of the family to be exactly the rate of growth of the number of minimal generators, then when the Ries algebra is Noetherian, or when the family is Noetherian, the two notions are the same. Unfortunately, in general, the two notions are not necessarily the same. In fact, even though this is always finite, this can be infinite. If we again start with the obvious family, the family of ordinary powers, or the family of symbolic powers, then this are just the familiar or the commonly known as analytic spread of the ideal, or the symbolic analytic spread of the ideal. And so let me go back to the polynomial ring setting. Again, if we have a polyhedron, then we're going to define MDC of the polyhedron, or for maximal dimension of compact phase, right? Then Vive Orsina proved that if you have a monomial ideals, then its usual analytic spread number is the same as one more than the maximum compact dimension of its Newton polyhedron. We were able to extend that result to any Noetherian family of monomial ideals, and it should be true for, again, any Noetherian family of NND ideals, that its analytic spread number is one more than the maximal compact dimension of its Newton Open-Group region. And if we restrict to symbolic powers, then as a corollary of our results, we also have that the symbolic polyhedron, symbolic analytic spread is one more than the maximum compact dimension of the symbolic polyhedron. So if we go back to one of our example again before, where the ideal generated by three monomials, x, y, y, z, and zx, and I've already give you the picture of two polyhedron, the Newton polyhedron and the symbolic polyhedron. The Newton polyhedron has one compact face, that dimension 2, that's a triangle, and so the analytic spread is 3. The Newton polyhedron, on the other hand, has compact faces of dimension that are being line, so the analytic spread number is 2 in that case. In fact, question that Long and Jonathan Montano raised, is that is it true that the analytic spread number is always bigger than or equal to the symbolic analytic spread number for monomial ideals? They of course state the question for more general class of ideals, but because we focus on monomial ideals, I'm going to restate the question for monomial ideals. So recently I have a current student who actually filed a counterexample for this question. So now the question should be stated as, for which monomial ideals does one have these inequalities? So this is an example. Again, the result that we had was for Noetherian family of ideals. What happened when the family is non-Noetherian? Unfortunately, in that case, example where the result doesn't hold. This is one of them. So we start with an ideal in with family of ideal in 4 variable, where the nth element just ab to the 4th times xy to the end. This is not a Noetherian family. The analytic spread number can be computed to be 0. However, one can figure out exactly what the Newton polyhedron of each family, each element inside the family is, and then if you scale by 1, take the union, take a closure, it's exactly this region here that has one compact phase connecting this point 0010 to the point 001 in R4, and so the maximum compact dimension will be 1, but that is not the same as the analytic spread number minus 1. So as I mentioned, so that this could be infinite, and this is an example why this invariant could be infinite. Again, this is an example in 4 variables. You can take any function fn, and for technicality, we're going to assume that fn is a non-decreasing function and is always at this end. And then we consider the family of ideals given by a to the 4th, a cubed, b cubed, b to the 4th. So we're missing a squared, b squared here, and then times xy to the n, and then we have a squared, b squared times xy to the fn. Then one can compute that the number of minimal generator for in is just fn plus 4n plus 5. So because fn can be chosen quite arbitrarily, that basically says that the number of minimal generators can have arbitrary growth. Right? So that's why this could be infinite. However, what we were able to prove is that even with this invariance, in some cases, we can connect it back to the Newton-Okunko region, particularly if we start with a gridded family of M primary homogeneous ideal, and we assume that the limiting body is a polyhedron. And we also assume, so again, this limiting body and Newton-Okunko body are now constructed with respect to good valuations. So there's no X here, right? And we assume that this good valuation respect the monomials in the ring R. One particular example of such a valuation is the Grobner valuations. Then in this case, this L star is still the same as 1 more than the maximal compact dimension of its Newton-Okunko region. And it happens to be exactly the same as the dimension R in this case. So any question before I move on to the next invariance?
No questions.
Thank you. So generally, I think that this what we call this formula here. Sorry, what we call this kind of formula is the unexpressed number equal to 1 more than the maximum compact dimensions should be true more generally, but for now, this is what we can prove. Okay, so next I'm going to move on to the invariance that we are also interested in, namely asymptotic regularity. This is just a quick review of, or quick recall of what regularity is. One can define generally, if we start with a standard gridded algebra over field K, then one can define the regularity to be max of P, such that when you look at the ith cohomology of this ideal with respect to the maximal ideal at degree P minus I is non-zero for some I. And thanks to result by David Eisenberg and Goto, we know that for the polynomial ring case, when the ring R is a polynomial ring, this invariant can be computed from the resolution by looking at the max of J minus I, where the IJ Bethe numbers of I is non-zero. So for a gridded family of homogeneous ideal, one can define the regularity or the asymptotic regularity of this family to be the limits of regularity of its nth element over n if this limit exists. So for the family of ordinary power, it is known that this limit exists. And in fact, it's already known that this regularity of I to the n is asymptotically a linear function. So when you take the limit of this regularity over n, you just pick out the first coefficient of that linear function. It is also known that that limit is the same as the limits of the maximal generating degree of I to the n over n. However, for the family of symbolic powers of a homogeneous ideal, it's still an open question whether or not the asymptotic regularity exists. This is a question by Herzog, Hua, and Chung in early 2000s. Now, generally, we know that the asymptotic regularity of a graded family of homogeneous ideal does not necessarily exist. And we'll see an example now. So this is an example that resemble, well, that we have looked at before. So again, we start with a function that is non-decreasing. And again, we assume that Fn is at this end. And we look at the family where the nth element is just given by almost ab to the fourth, missing out a square b square times xy to the end. And then we have this a square b square times xy to the f end. Then this example is the one that we know that for in, the number of minimal generators can behave arbitrarily, right, depending on the function f. And also for this family, we know that the regularity behave quite arbitrarily as well. So this is a graded filtration of monomial ideals, and the regularity can be computed to be Fn plus 5. So particularly based on the choice of Fn, this regularity can have arbitrary growth as well. So when you take this regularity divided by n and take limits, in general, that limit will not exist. So the question that we are interested in is, well, if we start with a graded family of homogeneous ideal, when does the asymptotic regularity exist? So when does the limits, when you look at the limits of reg of in multiplied out by n, when does it exist, right? And the next question that we're also interested in is, let's say that we know that it exists for a certain family, how do we compute them? Or how do we understand this limit? And relating to this talk, of course, how do we understand this limit from convex geometry, or from convex region or convex body associated to this given family? So regarding the first question, in a recent paper that I wrote with Herb Nguyen, who's in the Institute of Mathematics in Vietnam, and Tai Nguyen, my former student, we proved that if we start with any graded family homogeneous ideal, then the asymptotic regularity exists in the following cases. First, if the Riesz algebra is Noetherian, or if we start with a family of m primary ideals. More generally, if the family consists of ideals that are Macaulay of the same codimension. So that basically gives some answer to the first question: when does asymptotic regularity exist? And the next question is, well, if it exists, how do we understand? How do we understand it, or how do we compute it? And that, again, is closely tied to the notion of Newton-Okunkorp regions that we have defined. So here again, for a polyhedron, I'm going to set delta p polyhedron p inside R2D. We're going to set delta p to be the max values of the sum of coordinates of the vertices in P. So you take a vertex, you take the sum of the coordinates, take the max value of those. Then we prove first that, well, if we start with a Noetherian graded family of monomial ideals, so again, it's Noetherian, so we know that the limit, the asymptotic regularity exists. Now, if not only is a Noetherian family, but it's a Noetherian family of monomial ideals, and gamma is the Newton-Okunkorp region, then this asymptotic regularity is exactly delta of this Newton-Okunkorp region. So it can be computed from the vertices of the Newton-Okunkorp region. So again, let's look at an example. So this is a modified example of the one that we have seen before. The first component of the nth element in the family is still the same. The second component, now we still have a squared, b squared, but instead of x, y to some power, we now have x to the n, y to the n. This is a graded family of ideals. The Newton polyhedron has exactly two vertices given by 0, 1, 0, 0, 1, 0 and 0, 0, 0, 1. Unfortunately, this family is not Noetherian. And so when we compute the asymptotic regularity, we have 2 here. But when we compute delta of the Newton-Okunov region, we just get 1 coming from these vertices. And so these are not the same. And the reason here is the Rees algebra is not Noetherian. It does not satisfy our hypothesis. Another result that we can prove based on the notion of non-degenerates along coordinate axis. So let me first define that. So we said that a convex region is non-degenerate along the coordinate axis if each of its vertex of its vertices, if the vertices lives on any coordinate axis, then that vertex is going to be a limit point of a sequence, a point inside the limiting body. Remember that the Newton-Okunov region is just the closure of the limiting body, right? So every point in the Newton-Okunov region is the limit point of a sequence of points inside this guy. So this condition is basically say, well, if you start with the point, with the vertex of the Newton-Okunov region, and that vertex happen to be on some coordinate axis, then it has to be the limit point of a sequence of point of in here, but that sequence of point is also on the same coordinate axis. Okay. So let me give you an example. So this example here is an example where the Newton-Okunov region is not non-degenerate along the coordinate axis. So here we have the ideal, the nth element inside the family is given by the monomials whose exponents sit inside Pn, where Pn just the convex hull of 3 points, like phi n 0, 3n plus 1, 1, and 0, 2n. And of course, it's not very hard to see that this is a gridded family of ideals, because if you look at the sum of these two guys, it sits inside this guy. So Pm plus Pn sit inside Pm plus n. And if you check the Newton-Okunov region of this is the region. It has vertices being here and here. However, if you take the limiting body would be similar to the Newton-Okunov region, except that it's missing this light segment from 3 to 5. And that's because of these 2 points that we are looking at inside our family. So when we scale down by n, this has 3 plus 1 over n and 1 over n. So that's why it's never on this line for a limiting body. So the limiting body missed this line. And so if you look at the Newton-Okunov region, there are 2 vertices, 3, 0, 0, 2. Well, the 0, 2 here is the limit point of a sequence, a point inside the limiting body on the y-axis. But the point 3, 0, that is not the limiting body. Well, I mean, it is a limiting body of sequence of other point. But if you look at sequence of point inside the x-axis, those points are not inside the limiting body. So this point failed the condition for this guy to be non-degenerate along the x-axis. So this is not non-degenerate along the x-axis. And what we prove is that, well, if we start with a family of m primary homogeneous ideal, whose Newton-Okunov region that was constructed from a good valuations. And again, we always assume that the good valuation respect the monomials, and particularly we focus on the Grobner valuations. And we assume that this guy is a polyhedron that is non-degenerate along the coordinate axis to satisfy the condition that we have seen before. Then the regularity of the asymptotic regularity exists, and it's the same as delta of the Newton-Ogun coefficient. So again, it can be computed from the vertices of the Newton-Ogun coefficient. So let me give you an example here. So here, this is the example that we have seen. And because of this, we know that this does not satisfy the condition for being non-degenerate along the axis. And so we should not expect this formula to hold. And in fact, that is the case. If we compute delta, we have two vertices. And this is the sum of coordinates 2, this sum of coordinates 3. So the max of them is to be 3. However, if we compute the regularity, the asymptotic regularity is actually 5. And so in this case, without this condition, we do not have the equality. So that basically say that this condition is necessary for our result to hold. And I think that's a good place for me to stop. And if you are interested, this is what good valuations are. So basically, the condition for good valuation is that it has to be one-dimensional leaves, and it has to satisfy these two technical conditions. Thank you for your attention.
Thank you very much, Tai, for the interesting talk.
Thank you, Tai.
Thank you,
Are
Tai.
there any questions? Are there any questions? No, that's not the case. So again, Tai, thank you very much.
Thank you.
And the next talk in this series is on May 28th by Alessio Samartano.